Hi everyone, my name is Yan and this is my CFD final project presentation. My topic is flapping wing simulation. First of all, I will talk about the introduction of my project. This picture shows the structure of flapping wing aircraft, and we can see there are two processes, flap up and flap down, which provide the lift force for flying. The pictures at left is the simple model I designed in CAD, and I used a circle to represent the aircraft and aircraft fuselage, and the rectangle represent the first and second wing. This is my geometry. A large rectangle for air meshing was created, and this model was later exported into the ANSYS Fluent. This is the governing equation. Cause this is a 2D dimensional problem, so I cancel the 3D dimensional, and after that is my governing equation. And then come to the initial boundary conditions. I plan to set the condition at 2D dimensional, transit, and laminar flow. This equation is about the Reynolds number. Because this aircraft scale is not very big and it will fly in the air, so we assume the speed of the flapping wing at 1 meters per second. The air density is 1.225 kilogram per meters cubed, and the Reynolds number is 6.5 E6. The dynamic viscosity is 4.58 E negative 5 kilogram meter second. Next part is the mesh. In this part, I plan to use the dynamic mesh to see the motions about the second wing. In order to realize the motions, the way I choose is the oversight grid. We can see there are two zones. One is the background zone, include the fuselage and the first wing, and the second zone is the foreground, and it includes the second wing. In order to control the motions, there are two ways to use the user-defined functions. One is the complete, and another is the interpret. Because I only want to realize the motion of the second wing, so I choose the interpret way uh, to define the motion. I define the zone motion include name, omega, axis, origin, velocity, time, and dt. I need to set up the angular velocity and original coordinate, and then I will test this code to see the motion. This is the calculation about the residuals, and all the residuals values less than 1 times 10 to negative 9. And we can see the solutions run for 600 iterations, and every 200 steps the curves will repeat, so it is a period recycle. And then come to the velocity counters. This is the flap up process, and we can see the highest velocity come out at the right zone, and behind the wing shows the lowest velocity at the blue zone. The first picture is about the beginning position, and the second one is about the max position. the same thing. This is about the down process, and we can also see the red zone come out the highest velocity, and after the wings shows the blue zone is the lowest velocity, and this is the beginning position, and this is the maximum position of down process. From the velocity streamlines, we can see both the up and the down process. We can also see the recircular phenomenon. This is the animation after tightening the coils, and it can move. We can see the detailed motions of the wings. Next part is the my drag and the lift coefficient result. The condition is velocity at 1 meters per second, and the frequency I set is 2 Hz. We can see the CD curves. The range of it is from negative 0.3 to 0.3. This is the lift coefficient at the same condition, and we can also see the range from negative 0.3 to 0.4, and we can see both the drag and the lift coefficient is a period cycle, and we can see every 1 second we can see the curves repeat. This picture is by James Wang experiment result. We can see the tendency of the curve is close to my result, so that will help me improve my confidence of my result. Finally, I want to make a conclusion about my project. First one is the drag coefficient and the lift coefficient range also from include negative 1 to 1. And they will repeat every 200 iterations, so it's a period cycle, and it can fit with the real flap wing motions. The second one is the velocity counters. We can see there are velocity difference between the upper phase and the lower phase, and then they lead to the pressure difference, just like the Bernoulli equation. And also the higher position it is, the higher velocity it is. The third one is the streamline recircular phenomenon, and we can see the recirculation occur under the wing, and as the position going on, the recirculation phenomenon will turn more evident. Finally, we'll talk about some future works. The first one, I need to make some additional study on changes in velocity and frequency, and then I will add more group data to see what happened. The second is about the compare the drag and the lift coefficient at different conditions. Utilize the control a variable method. And the last one is compare the simulation drag and lift force values with the experiment data to see the error of my result. This is the reference. Thank you for your listening.